Hey, what's up, guys? Okay, so let's keep going about this admissible configuration. So previously I talked about this admissible configuration. So admissible configuration is a set of vectors in Rn such that there are in the upper half plane, so there is this H such that is phi subset of this, and their angle must there. So any two vectors, their angle must be pi over 2, 2 pi divided by 3, 3 pi divided by 4, 4, 5 pi divided by 6. And this is a collection of unit vectors. And then we just showed that simple roots forms admissible configuration. Okay, so in this video, my claims that these are all the these root system thinking diagrams are all the possible configurations which complete the classification of simple algebra over a finite dimensional simple algebra over complex number. Okay, so so I hope you guys already understand the admissible configuration. Okay, I also want to add a condition called irreducible. So we call the admissible configuration is irreducible if phi cannot be written as the non-empty two subsets, let's say phi1 union disjoint union phi2, such that any two vectors between pair will be 0, such that x1 belongs to phi1, x2 belongs to phi2. So for all x1, for all x2, x1 in the product with x2 is 0. Okay, so these are called irreducible. Basically, simply speaking, just that you cannot separate all the vectors in the admissible configuration into two parts, such that the two parts are also good. Okay, so our goal in this video is to show all irreducible admissible configuration are just thinking diagrams. Okay, so are just the diagram that we just it's a diagram that we want to prove. So let me. Okay, so let's I don't know. It's fine. Okay, let me just quickly copy this PowerPoint so that we understand what we are going to do. Okay. Okay. So this is our goal. We want to show that all the irreducible and admissible configuration are just inside this diagram. Okay, so let's talk about the meaning. Before we talk about meaning, let's tell you how to view this diagram. Okay, so this diagram is called called coexter diagram. Okay, so simply speaking, that if alpha and beta is negative half, basically their angle is 2 pi 2 pi divided by 3, then we will draw it. Then we will draw this alpha and beta. And if angle is this, if the angle is this, basically their angle is 3 pi divided by 4. We will draw alpha and beta. Sometimes we draw like this. So this directions means that the alpha is a length of square root to beta. But in our admissible configuration, we will do the normalization. So this is important. I just want to tell you that in the original simple roots, that if I draw it means that alpha is square root of beta. If I draw conversely, let's call this is alpha, this is beta. This means that beta is a square root of 2 alpha. Okay, and also for this is 5 pi divided by 6. And then we will draw something like this. And alpha is a square root of 3 beta, and vice versa. And if alpha is exactly 0, means their angle is exactly pi over 2, then we draw nothing. We draw nothing. Okay. So now you understand this diagram. So this diagram means that there are nodes, and each node, one by one, has angle between is basically 120 degree. Okay. Now you can read through all this diagram. Okay, so in order to prove that these are all possible, we need to like some main tool. Okay. So main tool. Okay, so tool 1. So tool 1 is a very trivial fact, is that what? So irreducible. So vectors in irreducible admissible configuration are linear independent. So this is our tool 1. So basically, our first tool is that all the vectors in the roots in these simple roots must be linear independent. Why this is true? You can try to. It's very interesting. Okay, so the idea is that suppose these are for phi I from 1 to n. It's not linear independent. Okay, so since they are all on the upper, they are all on some positive plane, right? So that means that you can separate. There is this AB, which is a subset from 1 to n, such that the summation CIVI, I belongs to A, is the same as CIVJ, J belongs to B. And all the CI, CJ are all positive because they are all on the upper half, they are on some upper half plane. Right, so these are all vectors. If you can find some subsets which there are sum to 0, there must be one part is positive, another part is also positive, and take their positives. But and also AB are disjointed. So AB are disjointed. Okay, but their angle is obtuse, right? So basically, what I want to tell you that is VIVJ is less than equal to 0 if I not the same as J. So let's tell you that CIVI J belongs to B, CJVJ are less than 0, less or equal to 0. Okay, so which tell you that but this guy is the same as this guy, right? So which tell you that I belongs to A, CIVI are all 0. But it's contradiction, because if this is true, this means that I belongs to A, CIVI, H are 0. But contradiction, because VI in the product with this regular vector is always greater than 0. And the CI are all positive. Okay, so it's contradiction. So vectors in the irreducible admissible configuration must be linear independent. Okay, second tool. Second tool is called the Bessel's inequality. So this is very simple. Suppose EI from 1 to n is also normal vectors. There are also normal vectors. So which means that EI, EJ are delta IJ. And so theorem is this: for any x belongs to, let's say this is in Rn, Rm. Okay, so if x belongs to Rm, then the length of x must be less or equal to x squared must be greater or equal to the sum of the projection. Okay, so why this is true? This is simple, because now these ER are also normal vectors, but they are maybe not a basis. So you can for example, you can write x equals to xei, I from 1 to n, and then maybe start from I from n to plus 1 to m. You just find the complement and find the basis, the also normal basis in complement basis. So you'll get something like this. Okay, you take norms that this x will greater or equal to the norm of this part because they are also normal. And notice if this equality holds. So if equality holds, means that x is x is span. So x is a linear combination. X is linear combination of ei, I from 1 to n. So this is most important. So if this equality holds, means that S is linear combination of this ei. So simply speaking, is that if you take E1, E2 up to En, and you take X, these are linear dependent set. Okay. Okay, so now we have these two powerful main tools, and we can start to try proof the Dynkin diagram. Okay. So first one is trivial, that the diagram must be a tree. Must be a tree. So irreducible and admissible configuration must be a tree. So tree means there's no cycle. So simply speaking, these type are not allowed. Also, these type are not allowed. Any cycle is not allowed. So basically, if you start from V1, V2, V3, maybe there's a this angle, or there's a this or whatever. Maybe you go V4, and you go Vn minus 1, and you go Vn. If there is a cycle, which is impossible, so no cycle. Okay. Proof. Okay, so this is very simple. Suppose I call it V1, V2 up to Vn, and what? Okay, so if I do this calculation, I take all the vectors and do sum, and I do the inner product. What will I get? So I should get so this Vi are positive, these Vi are normalized, right? So I should get n plus summation I j different from ji and Vi Vj. But since they are connected, right? So Vi and Vj must less or equal to half. Okay, so this tells you that these are less or equal to n minus half times 2 and n minus 1. These are half, and there are two terms. There are 2 times n. Let me think. So if n is 3, you will get the you will get the 6th term, right? So you get this. If n greater or equal to 3, then this guy will less or equal to 0. Correct? Because if n is 3, these are 0. If n is 4, this will less or equal to 0. So which tell you that this Vi must be 0. But this contradiction, because we just showed that they are linear independent, so they cannot sum to 0. Okay, so contradiction. Okay, so first one, I prove that Dynkin diagram must be a tree. Must be a tree. Okay. The second, if you have any nodes, can at most connecting 3 nodes. The degree. So any vertex in a coexter diagram. Coexter diagram has degree at most 3. Okay, so for example, this is degree 3. This has degree 3. This has degree 3. Okay, so this lemma, these results just tell you that, for example, if you want to do, if you're asking something like this, these are impossible. Okay, because this degree is 4. Okay, so this is 2, 1, 3, 1, 1, 1. So at most 3, at most 3. Okay, so proof. Let's call it V1. Let's call it V0. And then suppose it has V1, V2, V3, V4, maybe up to Vn. Okay, and we just calculate the inner products. We calculate the Vi with V0 squared. I from 1 to n. And by Bessel's inequality, this guy cannot be 1. If it's 1, that means that V0 is the inner, V0 is a linear combination of Vi. So this guy must less than 1. Okay, but this guy is Mi divided by 4, which is Mi is either 0, 1, 2, 3, less than 1. So it tells you that the degree at most 3. Okay, so which tell you the most, which tell you that G2 are the special one. If you have 1, 3 legs, there's nothing you can add. Okay, so G2 is a special one. It's the only one that you can add. You can add these 3. Okay. Now, I think once you believe this, then you are gonna to believe that ABC are okay. Okay, because ABC are good. Okay, so and D is also good because this is 1, 2, this is 3, right? So these are all possible. These are 3, 3. Okay, so I think up to now these are all okay. Good, good. G2 is good. So we are not showing that they are perfectly okay, but we just show that they don't violate the 2 rules, the two rules that we just proved. Okay, so now the problem is that why F4, E6, E6, E7, E8 are allowed. Okay. Okay, so next. So this is the F2. Sorry, this is F4. So what I will try to show is that F4 are special. F4 are special. Okay, so what this means is claim what? Claim these are not okay. So if this is 1, this is 3, this is 3, this is 1. So this can add 2, right? So what I'm going to show is that whatever you put here is not okay. Let me just talk the result. So what I'm saying is that these are not impossible. These are impossible. Okay, let's try to prove. This proof is interesting. So let me just think a little bit. How do I do this? Okay, so let's call this. Let's do this. Let's consider this diagram. Let's call this. Let's call this. U2 and the V3, V2, V1, and U1. Okay, and let's define a large U, capital U, 1 over square root of 3, U1 plus 2, U2, and the V is 1 over square root of 6, V1 plus 2, V2 plus 3, V3. Okay, for first I check that UU is 1 divided by 3. So U1 squared 1 plus 4 plus 6. U1, U2 is so notice that U1, U2 is by a single edge, so it's negative half. So this is 1. And you can also do the simple calculation. V1, VV is 1 over 6. 1 plus 4 plus 9 plus V1 and V2 are by half. 4. And the V1 and V3 are not connected, so nothing. And the V2 or V3 are connected, so plus 12 half. So these are also 1 over 6. 1 plus 4 plus 9 minus 2 minus 6. So it's still 1. Okay, so they are unit vectors because okay, obviously there are unit vectors. Okay, and let's also check. There's simple calculation that you can. So what is UV? So UV is 1 over square root of 18, and the U2 V3, right? So the only non-trivial is U2 V3, so it's 2, and the U2 V3. So what's U2 V3? So it's 2 divided by square root 18. U2 V3 is double edge, so it's this. Sorry, there's a 2 times 3, so there's 6. 6 is here. So this is 6. Okay, so this is minus 1. Okay. So now we have, oh, sorry about this. I need to add the more pages. Just a little bit. Oh. Okay, so we have UU1, UV minus 1, VV is 1. So which tell you that what? UV are linear dependent. Okay, hope you can see this by Cauchy-Schwarz inequality, because now UV are also normal, but their inner product is minus 1. Okay, so basically there are the vectors which are opposite directions. Okay, so which contradiction? Because if UV are linear dependent, basically it means that U1 V1, U2 V2, V3 are linear independent. So these are impossible. Okay, so F4 are special, and you can try to prove that if you try to add a double edge here, you also violate these possibilities. Okay. So let's make F4 very special. Okay. Now we are going to try to show another 3 possibilities. Okay, so these are also so this one is these are impossible. This is impossible. If you have single vertices, draw from this. So these are impossible. This is not yet show in our results because this is impossible. Okay, so let's call it X, and U1, U2, V1, V2, W2, W1. And then very simple, we define U to be 1 over square root of 3, U1 plus 2, U2. V is 1 over square root of 3, V1 plus 2, V2. W is 1 over square root of 3, W1 plus 2, W2. And your simple exercise is, as we proved before, that UVW are also normal. You can check by yourself. Now let's compute the inner product of XU1. XU will be square root of 3 half. But there's a U, right? So times 2. And also XV equals to XW is also this. So which tell you that the norm of X square is the same as XU square plus xv squared plus xw squared. So which contradiction? So because the reason is that by Bessel's inequality, so by Bessel's inequality, there are linear dependent. So x is linear dependent to this u1, u2, u3. So this is violate our results. So these are impossible. Okay, so I think finally, once I told you that you believe that A, B, C, D, and the G2 are and F4 are special. So finally, we need to deal with some strange case like so-called E6, E7, E8. Okay, so E6, E7, E8. Okay, so what is the E? Let's draw E6. Okay. So E6 is okay, but you cannot add here, right? Because we just proved that there you cannot add here. So add here is not okay. Okay, and you might think, and then, so you can try. Okay, I add here. Okay, so I can add here. Okay, so I'm very happy that I tried to add here. Okay, then this become E7 because 1, 2, 3, 4, 5, 6. Okay, and actually E8, oh, looks good, right? But I cannot do E9. Okay, so this is impossible. Proof. This is interesting proof. I don't know what who is the first guy who come up with this result. Let's say u1, u2, x, and let's do that. This is v. Let's call this v1, v2, u1, and w1, w2, w3, w4, w5. Okay, so that u to be u1, v to be 1 over root square root of 3, u1 plus 2 u2, and the w to be 1 over 15, w1 plus 2 w2 plus 3 w4 plus 3 w3, 4 w4 plus 5 w5. Okay, so let's do some simple calculation. So first, the u is 1, and the v is 1, and you can also show that w is 1. And obviously that the uv, so uv is not hit, right? So uv is 0, and the uw is 0, and the vw are 0, because they are not connected. So this forms also normal system, also normal. Okay, so now let's calculate x with u. So x will u will be half, negative half. Okay, and the x to the v will be 2 divided by square root of 3, and then there's an angle here, so negative 2, a negative half, so it's okay. Now let's calculate xw. So xw will be this one, right? So 1 over square root of 15, 5 times negative half. Okay, so if I do computation, I do this xu and the xv and the xw in the product with it, then I get the xu is half square. This guy is square, and then this guy is minus 5, 2 divided by square root of 15 square. So I do x3 square. Okay. So what should I get? I get the 1 divided by 4 plus 1 divided by 3 plus 1 divided by 25 and 60. Okay, so very tedious, but you get 1. Okay, so contradiction, because this guy will be the norm of x squared, which is 1. Okay, so this means that x by Bessel's inequality, this x is a linear combination with uvw, which contradicts the roots are or linear independent. Okay, so this is not addable. Okay, all of this. Okay, but we are missing one cases. So finally, right, this is all okay, but someone may try to add here. Okay, so this is impossible. This is our final proof. I think this proof is very interesting. So U1, V3, V2, V1, W1, W2, W3. So let's U to be U1, V to be V1 plus square root of V2. And W to be, sorry, there should be 3 terms. Okay, so obviously that they are all touched by this X, so they are also normal. So all these are also normal. Okay, so now let's do some calculation. So what is X U? What? Next U is negative half because there's a single edge. And X V3, sorry, X V will be 1 over square root of 6 and times 3 and times half. And the XW also the same thing. Okay, so let's add the square of it. So let me just write here. So XU square plus XV square plus XW square. 1 divided by 4 plus 9 divided by 12. 9 divided by 4 times, yeah, so times 2 times 2. Okay, so I get 1. Okay, so contradiction by Bessel's inequality. Okay, so this proof is stupid, but you can see that via Bessel's inequality that you can show that you cannot add here, you cannot add here, you cannot add here. Okay, so which proof that not E8 is special. Okay, so let me just summary. So first one is that the first rule is the coexter diagram. Coexter diagram has no cycle. Okay, and the second one is that the degree at most 3. And the third one is that these are not impossible. Sorry, these are impossible. And the fourth one rule is that these impossible, and also these impossible. And the sixth one is that this. So this is this is what we just showed. These are impossible, 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 impossible. Okay, so combine these 3, then you get E6, E7, E8. Combine these, you get special F4. Combine these, you get G2. And the previously combine 1 and 2 give you A, B, C, D. Okay, so these are classification of Dynkin diagrams and root system. Nice shot. Okay, so hope you can appreciate this video for some stupid guy which cannot find a professor, cannot find a faculty job. Okay, so hope you guys subscribe to my channel and see you guys next videos. Oh shit.